Hi all. I'm going to wait a little bit, maybe 1 minute before starting the presentation to give everyone the opportunity to connect to the event, and we are going to start after. Okay, I think we can start. So, hello everyone again. I'm very pleased to be with you today for this new Cailabs webinar dedicated to the incoherent beam combination with multi-plane light conversion technology. Today then we are going to speak about combination, of course, and the way to improve the power of your laser sources. We will dedicate a special part to the major challenges for this type of beam combination. How can such a combination be achieved while maintaining an optimal beam quality? A key issue for laser beams. If you have any question during the presentation, a dedicated space to that is available on the bottom right side. And do not worry if your question does not appear. And if I do not stop the presentation for it, I will display and answer them at the end of the presentation. And of course, if you will have new ones after the live show, feel free to contact me. I will be happy to help you after. So, but as always, let's start with a short introduction about who I am. My name is Tanguy Guinic, and I'm a product manager at Cailabs. I'm in charge of the Proteus product, product for telecom application, and also the new applications that we are interested in at Cailabs. I have a background in physics and a specialization in optics, and I have had professional experiences in various sectors such as aeronautics, robotics, or biotechnology. About the program of this webinar, I plan to begin with a short explanation about who we are at Cailabs and what are the Cailabs tailored optical solutions that we can propose. As I speak about laser combination, I would like to spend some time on the reason we have to combine laser beams. I will explain the special features of incoherent combination and what is our approach at Cailabs to achieve it with our technology. And finally, I will present the combiners that we can provide after discussing two examples of applications where this type of combination can be used. So firstly, what is Cailabs? We are a deep tech company. Cailabs developed a few years ago a unique patented technology, which is the MPLC as multi-plane light conversion. And more generally, we are experts in beam shaping. We are now more than 50 with 20 PhDs, and we are in capacity to develop, manufacture, and sell innovative optical components. We are located at Rennes, in Brittany, in the west part of France. And since last year, we also have a sales office in the center of Paris. As I said, our expertise is beam shaping, but what we call exactly with beam shaping and what we can bring, you know that it's possible to play on several properties of the light, like the power, the wavelength, the polarization, and the phase. And at Cailabs, we allow the addition of new degree of freedom, which is the shape of the light. To give you an idea about what we can shape, these are examples of shapes that we already realized. In the left side with only one monomode transform, and on the right side with several mode transform. And at Cailabs, we like to use mode for realize some complex shape. These skills have a lot of area of application, and we developed a range of products around our complex beam shaping expertise. Let me present them briefly. First, we have on the left side the Canunda project range, which is specialized into the improvement of industrial cutting lasers. We have after the Aruna product. Aruna proposes to improve existing legacy network. Tilbar is dedicated to the free space satellite laser communications. Proteus, which invent the networks of the future and propose some kind of space division multiplexer. And finally, we have Custom, which is not a product, but where we enable tailored optical solutions for specific development in defense, aeronautics, automotive, sensors, or biomedical. Our Cailabs combiners are part of this last family. What are the Cailabs tailored optical solutions? We can summarize it as technical function divided in three main categories. At the emission, we can combine or multiplex laser beams. As beam shaping expert, we can also change the spatial shape of the output beam to realize a top hat, a line, a star, or a donut, for example, with optimal performances. And finally, we propose several functions to optimize or analyze the beam reception of an optical system. And this is a list of all the functions we propose. You can find some information about them in our website, but today, as we are talking about incoherent beam combination, I'm going to select the combiner function. And I'm going to go deeper in the presentation about incoherent beam combination. So firstly, why do we combine laser beams? The limited power of laser is a real problem in many areas. The beam combination allows to increase this power and also to use standard sources on the shelves compared to bigger one or more custom one. Because they are more sold, they are generally also more tested. And in the list below, there's example where we need high power laser sources. Of course, material processing, use the ones for industrial welding applications. The fundamental science experiments, such as laser-induced nuclear fusion, is another application. In defense area, incoherent beam combination is also interesting to deliver much power for countermeasuring application or directed energy weapon. And finally, to deliver more power at 1550 nanometers or in the mid-infrared range for laser communication, have also an interest to investigate these topics. Now, what are the main challenges of beam combination? The issues at stake are therefore identical to those of single laser sources. Firstly, it's of course to have a good electro-optical efficiency to maximize the power output of the combiner, because it's the main challenge. Secondly, it's to maintain good output beam quality to ensure good propagation of the output beam while concentrating the energy in a specific location. The stability of the component is really important. If the system moves, because it's impossible to manage such a power, it's not useful. And to have a small component is also important if you plan to integrate it into a real small system. And finally, it's also a complex trade-off between N, the number of inputs you would like to combine, and P, their individual laser powers. Because as you will see in the next slides, the more power beams they are to combine, the more difficult it can be to do it. Right now, and before to go deeper in the explanation of our approach to realize the incoherent beam combination, it's important to remember that there are two ways to combine light. There are the coherent beam combination of light for sources with very small spectral widths, and the incoherent beam combination for the rest, and that we are going to discuss later. Both techniques are compatible with our technology. If you would like to combine currently the sources, you have to control the wavelengths, the phase, and the polarization. The advantage of this technique is to obtain a really beautiful output beam quality, but the phase locking stage is not so easy to realize it. The combination method is based on using constructive interferences. One of the main advantages of the incoherent beam technology is that you do not need these controls in phase and in polarization, and it's just an additive superposition without interferences. As you maybe already understood, you can realize it by passive means without a phase controller, without active sensing and control, which is the most complicated things to do with coherent combination. And for incoherent beam combination, there are different possible methods. You can, for example, overlap several laser beams without control of the wavelengths or polarization. This is what we choose. I'm going to explain how we do it after. And you can realize a specific wavelength beam combination with a diffraction grating component. It works quite well at low power. It consists to spatially overlap beams of different wavelengths. The alignment of the beam is really difficult because you need to be at a specific location. And this diffraction this diffraction grating component is limited also by the stability at high power, but I will not detail more this technology, and I'm going to switch directly on the first method. To finish my introduction on the incoherent combination, we can say that the main challenges for it is to maintain a good quality output beam, and the ability to combine a lot of sources is also a real challenge. And finally, it's not easy to align. Is it easy to align? Is it stable exposed to high power? Are also important questions. So our approach at Cailabs is based on multiplane light conversion technology, a technology patented by Cailabs in 2010. MPLC is a reflective technology and a passive optical process whose principle is derived from quantum optics. The idea is, with a succession of faceplates and free space propagation, we have the ability to transform any kind of Gaussian beam in whatever we want, as soon as it's a unitary transformation, a unitary basis into another unitary basis. If you want more complex shape and multiple beams, mathematically they always have a solution to modify this shape with more faceplates and free space propagations. And if you have to do that in transmission, you have a lot of losses and it becomes complicated at high power. That's why we decided to have the device in reflection. So we realize a unique texture surface that you can see in yellow on the right side. A unique faceplate, and the free space propagation is done with the help of only one mirror. You can have much more inputs. You can combine them or divide them into only one or separate channel. So we have several optical fiber at input. We modify each input with the faceplates and the free space propagation until the output of the component. We can modify the fiber elements to free space optics, and you can have a lot of different configurations, which corresponds to different applications. So you understand that you can do a lot of things with these components, such as combining beams. This, on the left side, is a top view of a special multiplexer for telecom application, where we already proposed the ability to combine up to 45 input channels into a multimode fiber. You can see the 45 Hermite Gaussian ones in the right side pictures. So the Cailabs solution for incoherent beam combination is also a modal approach. Firstly, the important things to know is that for this kind of application, we cannot combine single mode inputs into single mode outputs. The laws of physics will not like it. If you are interested to know why, I invite you to read our blog article about it, written by my colleague David Aliou. The idea is also to convert each input into a specific spatial mode. The linear combination of this converged mode will give the final output beam that you can see on the right side. In this present example, where we combine 4 input beams, we convert them into a specific LG mode. LG has a Laguerre Gaussian mode. Input 1 into LG00, input 2 into LG10, and so on. And as you can see, the final output beam is the real sum of the 4 inputs. Now we are going to see why this approach is unique and why it's a state-of-the-art approach to obtain a really good output beam quality. Because with this approach, the M square value, which corresponds to the quality of the output beam, will be still proportional to the number of inputs, but it will increase much more less than with other techniques. In the table on the right side, you can see that for 10 combined laser sources, we obtain a theoretical M square equal to 3. And in the graph on the left side, you can see that the overlap of the 10 modes is really good compared to the perfect Gaussian beam, which is the best one. It is a fundamental mode. And on the right side, you can see in the graph that our combiner is really well positioned in the market thanks to this model approach. We are really close to the theoretical limitation, which appear in gray. So at Cailabs, we can provide a compact combiner already aligned inside a box that you can see on the two pictures on the right side, an input fiber component and a fibered or free space output, compatible with a wide range of wavelengths from the visible to 10 micrometers, with optimal output beam quality and an optional custom beam shaping option. It can be at the output a top hat round, a square, triangle, line, star, or donut. And this additional function, yes, can be implemented at the output of our system. To meet the customer power requirements, we propose already a list of products available for your project for incoherent beam combination. It's divided today in two range of wavelengths. In the mid-infrared one at 1 micrometers, I will explain after two case studies in the next slide for each range. Customization are of course possible. For example, we have in mind new targets to develop kilowatt combiners at 1 micrometers in 2022, 2023. And to finish with this table, you can see that we validated interesting combining efficiency. Important thing, coupling losses, the input fibers are not included, but we have also a high expertise to realize this injection into a fiber if you need so, thanks to our experience into fibered components. Now, I would like to present two case studies. The first one is also QCL's incoherent beam combination for countermeasure applications. For such defense products, there is a growing need of energy to provide powerful sources in mid-infrared for countermeasure systems. The countermeasure system is a protection against the threat of self-guided missiles. It consists to put a lot of light into the reception area of the missile to remove its attack and make it inoperative. And customer need is a technology challenge to achieve a high power and low divergence beam. Why low divergence beam? Because it's important to have an optimal divergence to accurately guide the emission. QCL as quantum cascade laser sources are really interesting candidates to build these sources. They are really promising laser technology with standard components already available on the market. They are quite small, stable, but they are limited to 1 to 2 watts, and they are not so easy to couple in an optical fiber. So the Cailabs solution for that is a real know-how to inject a QCL beam into a fiber, a passive solution to provide an output power of 10 watts, an optimal quality factor around M square value close to 3.5 for 6 QCL. And I invite you to assist to the next SPIE Security and Defense show in September. We will present the performances we are obtaining in the context of a project funded by the DGA and the French Defense Innovation Agency on the subject. If you would like more details. Cailabs is working also on projects about direct energy application where the aim is to have enough power to damage a drone. And at these wavelengths, around 1 micrometers, the challenge is to obtain the best combination efficiency to provide something small in order to be embeddable in the future. Last months, we worked, thanks to the DGA, on the project managed by the French Aerospace Lab, ONERA, into the development of an incoherent combination of 4 times 100-watt laser sources at 1 micrometers. And we validated a mean transmission rate around 92% and an M-square value between 2 and 2.3. The potential improvement of this technology are really high, and we have, as I said before, the target in mind to increase again the input power of our system to propose some kilowatt combiners. For other products, we developed an internal know-how to propose components compatible with aircraft environment, and 16 kilowatt with a different approach have been validated for laser processing applications. To conclude this presentation, we can summarize the Cailabs approach as a new component, a new way, a new possibility to realize an efficient incoherent beam combination, which propose a really good output beam quality with a really good efficiency in a compact component, stable, and of course easy to use thanks to the fibered input. So I finished my presentation. Thank you all for your attention. It's now the time of question. If you have ones, I will display them right now in our screen. Okay, so you don't have any question. I invite you to ask them if you have ones. I will be happy to help you if you need. Yes, feel free to write me into this email, tanguy@cailabs.com, and thank you all for your attention. Bye.